time scale is in coastal scale. In the east coast of the United States, we call it FRF, Field Research Facility. It's located in North Carolina. And we measure along a transect from 2 meters to 27 meters. And every week, we also go to the field, my colleague, and they collect the topography because the bathymetry also changes. And we model all of these things. So we model the water level, the wind, the atmosphere, the wave, the combination of all of them, and we validate our model with the observations. And we have this facility for nearly 30 years, so all of the numerical models are calibrated with this facility because there is no other competitor in all around the world. And if you look at one of the sample examples of the spectrum, but this time not just in frequency space, also in durational space, you can see waves are coming from different directions with different frequency. So that's the complication of the issue. Some very basic things about what's happening to the waves. So we have wave shoaling, which means if waves are coming perpendicular to the coastline, they tend to increase their height. So if you consider tsunami, for example, tsunami in deep water is about a few centimeters. So nobody noticed them until they get closer to the coastline because wave wants to keep the energy, but they started touching the ground, and it doesn't want to lose the energy. So instead of losing the energy, it decides to lower the speed. So the phase celerity goes down, but the height goes higher. So that's why when tsunami reaches the coastline, the size of the waves from a few centimeters goes to a few meters. And the longer the wave is, the shoaling, it's more pronounced. So you can, because the wavelength is longer, so it touches the bottom earlier and it starts growing. So this phenomena is called shoaling, and it's very famous. So there is a historical, in the literature, there are many graphs that does explain how shoaling works. But this is the shallow water region, and this is the deep water region, and this is the shoaling. H is the wave height compared to the H0, which is in deep water. And C is the phase celerity compared to the phase celerity in deep water. L is the wavelength compared to the wavelength in deep water. So as it gets closer to the shoreline, to shallower water, it becomes larger and larger. Depends on the wave frequency and the dispersion relation. This is another schematic showing that in deep water, the wave orbits doesn't touch the bottom, right? So it's like a circle, and then as they get closer to the coast, then you can see the speed goes down, the velocity decreases, and then the height increases.
Sorry, can I just ask that?
Sure.
So you're assuming that the bed of the sea is kind of becomes
shallower.
Yes.
Okay.
Uniformly. Is there a chance that it might actually go and then suddenly
yes, so that's the reality, right?
Thing and then it goes
yes.
up again. So what happens then?
So most of the time, waves breaks way earlier than such a thing happens. But that's why we don't have this very super simplified condition, right? So in nature, we have also having some trenches, but usually in deep water, when the waves comes to the coastline, such phenomena is observed, right? So I mean, the shoaling happens, and then also wave can break. So wave cannot grow unlimitedly, right? So at some points the waves breaks. This is the thing that you guys also see in the seaside, right? So if the height of the wave is large, wave overtops itself and it breaks and releases the energy, right? So if that doesn't exist, then all of the wave energy would collide the coastline and erode everything, or cliffs or everything, right? So it's not happening because many other mechanism comes and dissipates the wave. So if we have a trench from deep water, so for example, if you have this side and then it goes down, based on the linear theory, so the wave height cannot decrease. So it continues with such a speed, and it doesn't change also the height. But if it again goes shallower, it starts shoaling. But many other processes that I'm going to show you in the following slide also take place. So you don't see, it's a combination, it's very complicated. And that's why we have numerical models. So wave refraction is another physical phenomena that happens. Waves also follow the topography, right? So we don't have such uniform increasing or decreasing water depth. They also have some variability in depth contour. So imagine you have such condition when waves are coming oblique. So these part of the waves are getting closer to the coastline, right? So they want to touch the bottom earlier than the waves are going this way, right? So this part slows down, this part still continues with the same speed. That's why most of the time, if your beach slope is smooth, even not uniform, you can see most of the waves are coming to the coastline eventually perpendicular, normal to the shore. So you see this part turns, and then at the end, all of them are shore normal, right? So this is refraction. So this is the contour that happens. So imagine this is the depth contour, and then this part is about to reach the coastline faster compared to that part, so they start to refract. So you see most of them are becoming shore normal at the end, okay? Beside that shoaling event that I explained. So you can, if you want to super simplify it, it's like the Snell's law, so you can calculate how they refract towards the shoreline. And this is one example, a typical shoreline, so you don't have just a straight shoreline, so you have the divergence and the convergence of the energy of the waves. And this helps people, for example, in Netherlands, when they want to trap the sediments, they know all of these physical things, right? So they put a groin here, and they know, for example, a longshore transport is happening there, so they trap the sediment also there. So they make it longer, and then they dissipate the waves more, and then they drop the sediment. So all of them have some engineering application down the road. But, I mean, we are not talking about engineering application here. It's mostly about science. Also, we have this phenomena when I think it's very similar to analogy to the light. So if you have a sudden change in the wave propagation, then you also see such phenomena. And it's very pronounced in the entrance of the harbors. So waves are shore normal, and then when they enter, they start to radiate away. It's circular, right? And then wave reflection. So like any other wave that reaches some solid boundary, then they start reflecting back. But it's not like a vertical wall, so the majority of the energy got damped on the way. The wave breaking happens, but some of the energy reflects back to the ocean, right? And for infragravity waves, which are longer waves, they happen more compared to the short waves. So it depends on also the frequency. Yeah, this is very schematic. You can have, if it's an idealized situation, then you can have a standing waves if you have a full reflection from the wall, right? And this can be observed in the flume easily. Sometimes people does it to study the wave-wave interaction, and then they do such analysis before conducting the simulation. But most of the time, energy got damped with friction and many other physics. Also, we have wave breaking. So waves cannot grow unlimitedly, right? So they break at some point. So Stokes waves, and then I think Mike, he suggested this is the condition when the waves starts to break. So, and this is a very valid condition. So it depends on the depth of the waves and the frequency of the waves, wave starts to break. So the whole energy doesn't propagate. And that's why in the coastline, you can see wave breaking. In the offshore, you can less wave breaking. But also in deep water, it can happen. Okay, so what we do from an engineering point of view, we model them, but we cannot simplify everything to go and solve them analytically, like what you guys do. Instead, we have to solve them numerically. And there are many numerical models that can handle the situation, but they come with different computational costs. Okay? So we have phase average model that should just concentrate on the wave energy propagation, dissipation, source term, etc. Or you want to resolve all single details of the time series. So that's the phase result models. If you compare these two models, this one can run on global scale. They run faster on the same configuration. This phase result model, they run slower, but they give you a detailed description of the sea state. So if you want to design a hardware, you need to go with phase resolve. But if you are predicting or doing some climate analysis, then you cannot afford computations for such long simulations, so you go with the spectral wave model. And this is the model that I'm going to show you today. So spectral wave models like WaveWatch that I developed, these are means to use for climate analysis, for the forecast, but they solve the wave action balance equation. We are not talking about the time series. Everything is in the frequency space. So this is the equation we solve. So energy in time, change of energy in time. This is the propagation part in the direction. And the source term and the dissipation terms are also on the other side of the equation. So the source term is like the wind and other mechanism that generates the wave, and dissipations are just depth breaking, triad interaction, and many other coastal processes that happens. So all of them together, we solve them numerically on a numerical domain, and then it already includes the diffraction, refraction, reflection, and physics that we want to implement. So all of them are added to the sink term or the source terms. I think that's something similar. N is energy, and then I think I should skip to keep the path of the presentation. So the physics are in these two formats, the sink term, source term. This is the propagation part, which is in space and time. And then this is the energy in time, the derivative of that. And we have different source terms. So in this presentation, we're going to focus on the wind side. So wind blows on the water surface, and they generate the waves. If the waves is generated way away, they propagate like swirl, and the wind waves are generated locally, but they interact with each other coming from different directions. Also in the ocean, they interact with the current and water level variation. And then you can have other factors that also play, like the precipitation. It decreases the drag coefficient. So if you have two equivalent conditions, but the wind is blowing when it's raining, it's different. The drag coefficient is different. So we also consider those to compensate the difference between these physical phenomena. All of them are integrated in the numerical model. WaveWatch III is a model that is the development that started in the 90s at NOAA NCEP when I used to work. And then in 2017, when I took the charge in terms of the development, we modernized the code. So the original WaveWatch was meant to use for global scale applications for coarse resolution simulations, like 20 kilometer, 50 kilometer, something like that. When I came on board, we added the unstructured capability, which I will show you momentarily. The unstructured capability will give you some opportunity to go very fine scale, like coastal scale, a few meter resolution, and then you can see all of the coastal scale phenomena and physics there. So since 2016, we modernized the code, and we added coastal scale physics, like the reflection, shoaling, etc. And this model is widely used with all the numerical prediction center, like ECMWF, European Center for Medium Range Forecast, by UK Met, by US Navy, US Army, French Navy, Australians, Italians, all around the world. There are two major numerical models used in forecast centers. One of them is WaveWatch, the other one is WAM. So these are the two major numerical models that people use, and we have lots of users and developers from all around the world. So that was the introduction, and I added them to this presentation just to have you on board with what we do. Now I want to show you what's the engineering application of this for coastal scale and during hurricane seasons, how this model performs, and how we quantify the performance and the results of the model with observations, what type of observations we have, and all of them are in this presentation. So because we work for forecast centers or operational center, also we need to automate our system, so we need to minimize the human intervention in the computations. And imagine all of these things happen on a regular basis, 24/7. So for example, this system that I'm going to show you, it's running every 6 hours, and it predicts for 2 weeks. So we cannot sit there and hit the button and run the simulation again and again. Instead, we modernized it and we made it fully automated. So every 6 hours, it does the prediction from scratch, and it does it on its own. So it doesn't need any human intervention. So that's a part of the workflow that we do, And I think with Osama, we are also doing the same thing for the tsunami. So no human touching the bottom, but whenever there is happening something in the ocean, then the model is triggers. But for wind waves, it's running forever, so it never stops. And then we collect the topography, the LiDAR data, what's the sea level rise projection, what is the wind forcing, what is the water level forcing, what is the current forcing. And then we have a mesh generator, which we call it Okeanos. It generates the unstructured mesh. It runs the wave model. It exports the outputs, and it validates it with observations, and it populates it to media. So all the news that you can see from UK, but in the media, from the wave side, it's coming from WaveWatch, following something similar, but UK may develop that workflow, but the core model is WaveWatch that I'm going to explain to you how it works. Everything is open source because US taxpayers paid for that. So WaveWatch source code is located in our GitHub repo. We have pre- and post-processing scripts which does the pre-processing for data preparation. We blend different atmospheric forcing. The blender is there, and we also can optimize the physical parameters in the model, so all of them are on GitHub. And I'm going to show you a couple of applications in Great Lake, in Oregon, in the west coast of the US. Some studies we did for wave-vegetation interaction, wave-triad interaction in France. Hurricane season 2022, which I will focus more. These types of observations with satellite altimeters and buoys and drifter buoys. And then I will conclude at the end. So in terms of mesh generation, we wanted to have an unstructured mesh. Unstructured mesh are triangular meshes that can vary the resolution. So as they get closer to the coastline, they are finer resolution, and offshore they are coarser, because in offshore, all of those sudden changes never happen. So we can safely make them coarser, and as we get closer to the coastline, we make it finer resolution. So you can define some boundary condition and criteria for the mesh generator, and it's also fully automated. This is one example. So you see all of these triangles, and this is a very high resolution mesh, so you cannot see the triangle, but as they get closer to the coastline, they become finer to resolve the topography in those regions. This is in Marshall Island in Pacific. We also have some numerical artifacts. So this is one of the forecasts that NOAA generates with the previous generation of WaveWatch, which doesn't run on unstructured. This is the old version of WaveWatch. So this is Hurricane Lee in 2023, and this is the wave height reaching the east coast of the United States. So all of these straps that you see, they are artifacts, they are not realistic. So the old model also had some limitations in terms of these artifacts, and we are trying to get rid of all of those. So this is the unstructured part of WaveWatch, and then this is the structured part, the old version. So you can see all of those artifacts, and with this correction in the dissipation terms in the numerical model, solving these tensor, then you can get rid of all of those artifacts. So we fix the problem here. In terms of physics optimization, this model is still simplified compared to the reality. So we are not solving the full Navier-Stokes equation, right? So we have to also optimize some of our coefficients, because sometimes the wind, the forcing is biased, or sometimes the physics is not capturing the entire physics. So sometimes you need to fine-tune some of the parameters. So we developed the optimizer which does the job iteratively. So it does the simulation, it sends it to optimizer, which is the mathematical solver. It gives back the optimized variable, it reruns again, does the analysis. If the bias goes lower, then it keeps doing it until one of these stop criteria happens. So, I mean, all of this happens to make the model more accurate. And this is engineering approach again. So we know that the models are not perfect, but we can make the model closer to the observations. That's the work that we engineers do. This is one of the applications we implemented at NOAA in Operational Center. So this is Great Lake in the US, and then we implemented last year an operational version of WaveWatch for wave forecast. And then you can see, this is the scalability plot, but you can see the performance of the model. The observations are black, and then the blue is the model, also the magenta is the model. So we are matching the observations very well. Also, we generate some plot called Taylor diagram. I'm not sure if you are familiar with that, but it's a nice way to compare standard deviation, correlation coefficient, and root mean square deviation. So the closer to this point, the better, more accurate. And as it goes further, this is the correlation coefficient. Then as it goes from these circles further, this is the root mean square deviation, and then the standard deviation also is on the x-axis. So you can compare three statistics on one plot. And this is what weather forecaster usually use to show the performance of the model. Because usually I have to explain Taylor diagram to people who are not familiar with that.
So, sorry, is your model stochastic?
Yeah, it can be, yeah. This is the second testbed that we recently started in the West Coast because the East Coast was prone to hurricane cases a lot. And since Hurricane Sandy and Katrina before that, US invested a lot on the East Coast. And that's why we had that North Carolina testbed. Recently, Pacific Ocean also becomes an interest for many, many people, also including NOAA and Army Corps of Engineers. So we started the second field study in the Oregon state, which has a different wave climate. It's mostly swell dominant compared to the East Coast, which is hurricane dominant. And we are doing the same thing that we have been doing in the FRF. So this is some studies that we have done there. We quantified the wave model there. And like many, many other applications, we are progressing with the advancement in the technology. So this is happening in parallel. So you have numerical models, and you have them before this as well, right? But computers were not capable to run very complicated physics or very high-resolution models, and the parallelization also was a problem. At the time I joined NOAA, we have been running the wave model on around 1,000 CPUs. Now they are running the forecast model on 12,000 CPUs. So you can see, and CPUs are also faster. So I mean, it's a big boost in the computational resources and their speed. So we had to also move together with them. And that's why we are working on improving the numerical model, also on the performance and the efficiency of that. So we can keep the pace with so for example, recently we are also thinking about GPUs because we can use GPUs to do the simulation faster, and it is going and going. So this is a parallel thing. We increase the resolution, computer scientists provide us faster computers, then we start thinking about, okay, let's go finer resolution, and they give us again another better computer, and it goes forever. So I mean, we should just keep the pace with all of them and progress together. So this is what's happening in our scenario. This is wave modeling in wetland. In the US, after, I think, Second World War, they started realizing vegetation can also damp the energy of the hurricanes without having any hard structure that they used to build. So some time ago, they used to destroy the wetlands. And these days, they are restoring them because they know how valuable they are. So, and we wanted to see if our model also is capable to capture the wave and vegetation interaction to see the damping phenomena. So this is a study we did in 2017 during Hurricane Maria. We observed, we put some wave gauges on the wetland, and you can see the wave vegetation interaction in this animation. And then we also coupled our wave model with a circulation model. The circulation model provides the tidal changes and the currents. So the model also can see wetting and drying, because when the hurricane comes, the flood goes to the marshland and it overtops everywhere. So waves also can generate on that tiny piece of water that is flooded on the marshland, right? So we had to come up with this coupled application where two different earth systems, a wave model and a storm surge model, can talk to each other. And then we did the validation. So we put the gauges, this is the coastline, and during that flood in Chesapeake Bay 2017, the entire marsh got flooded, right? So this is the comparison between the model outputs, and these points are the observations, the significant wave height, without vegetation, wave vegetation interaction, which you can see there is a big bias between the observations and the model, and this is the one with vegetation. So you can see the colors are more or less identical. So it means the model could capture the wave vegetation interaction. And this is the time series. So you can see as we go from offshore to near shore, the green line is the model outputs with the vegetation, and the observations are blue, so they are matching each other. And if you don't consider vegetation, that's the magenta, which is far biased, right? So, I mean, we are quantifying our model with either time series or with some satellite data, but in this case, we don't have satellite data. Wave triad is another important piece that we consider. So, in this case, in France, they deployed the gauges, and they wanted to see the wave triad interaction. And then we could capture it with WaveWatch, the same way with the observations. Next, let's quickly move on to the Atlantic 2022 hurricane season, which was the third deadly and destructive hurricane season in the history of the US. We had Hurricane Ian, which was very famous. It washed a part of Florida, and we had to evacuate people from Florida. So this is the amount of the money that each of those hurricanes in that hurricane season made problem. And these are the hurricane tracks in the Atlantic. What types of observations we have? NOAA deploys NDBC National Data Buoy Center observations. These are the size of the buoy, they are gigantic. And they measure directional wave spectrum. Satellites also collects the sea surface, and we can also utilize them to validate our model. And recently, commercial companies came on board. I think that should be an animation. Yeah. So a company in San Francisco started developing small buoys. You remember the previous study, it was gigantic. They are building such size buoy, and they drop it in the ocean, and they drift, and they are all around the world. So if you compare it with the NDBC network, this is a lot. It's way cheaper, and it's a great source of observations that we can validate our model with. This hurricane season, so these lines are the satellite tracks, which are coming every day. These magenta points are NDBC network, and the red points are the drifter buoys. So this is moving in time, right? So we have a big set of data to validate our model, and this is static snapshots of all of them together. And these are the buoys that we are using. So we have a rich data set, like 1.1 million satellite data and 165K stationary NDBC and 36K drifter buoys. So in total, 1.3 million data sets that we can validate our model. We prepared the atmospheric forcing to run the model from different resources, and then let's talk about the validation. So I explained the scatter plot for the Taylor diagram. We also do the scatter plot to show for different percentile how the model performs. And then we also do the QQ plot, quantile quantile plot. And all of them, we do them for the wind speed, for the significant wave height, for mean wave period, for peak period, and for the wave direction. So all of them are quantified in that way. So this is the quantification of the wind speed and wind direction at the NDBC location. So you can see we have a good agreement from the atmospheric model. And this is for the satellite data. It's also showing promising results. And then we run the wave model. So we run the model for multiple directions, and we discretize the model for 36 direction and 35 frequency, covering swell and wind component. We generated the mesh, which has 2.3 million nodes, global scale. So that's a very high resolution mesh, and we ran it for the whole 6 months of 2022 hurricane season. And then we did the validation. So this is for the satellite data, the same story, but we ran it on one coarse resolution mesh and one fine resolution mesh. So if you remember, I told you if it gets closer to this point, to 1 and 1, then it means it's an improvement. So you can see, compare these two together, this scatter cloud moves towards better agreement. The QQ plot also tends to be better, and the scatter plot also shows some improvement. Overall, the satellite data is showing us promising results. And let's look at some detailed time series analysis. So I told you about we have directions and the frequency spectrum energy density. So I'm not sure if you can see all of these subplots, but imagine this box. This buoy is located here, and these are the hurricane tracks. This is the observed observed a spectrum, a spectral density, and this is the model. So you can compare them qualitatively. And if you want to compare the time series, you can see this is the significant wave height, observation is red, and model is blue. So you can see it captured the entire time series. This is the peak period, the mean wave direction, wind speed, mean wave period, and wind direction. So we are also comparing the spectrum and the time series to some extent. And then another locations, so you can see we checked all single point that we had to make sure the model does its job offshore, near shore, in shallow water, behind some barrier islands, everywhere. Wherever we had observations, we compared the model to make sure the model is not missing anything. And then this is the summary of that. So for coarse resolution mesh, we had some underestimations. With the high resolution mesh, we captured almost everything, compared this part to this part. And then you can see even for higher wave height, we are capturing everything very well. This is for the mean period, so I'm not going to spend time on this one, but overall I want to give you the idea we are not just comparing the significant wave height. We have to make sure we are capturing the period, we are capturing the direction, and in different locations. This is the fun part because recently these drifter buoys came to the market, so we are trying to utilize all of them as much as possible. The red line is the path of those drifters. So if you see some drifters rotating like that, because the Gulf Stream is taking them in the Gulf of Mexico. So they dropped it there from an airplane, and during their deployments, the Gulf Stream took the gauge and moved it around. It's not stationary, it's not moored to the sea bottom. And then the same story. So you can compare the spectrum or the time series and come up with the statistics. So this is more pronounced because it was there for a longer time, and you can see how crazy the drifter moved. But it is very critical for us. We never had observations in such location, and now we are more confident about how the model is doing because of these types of observations. And luckily, the number of observations are growing exponentially these days. And other examples that I'm not going to explain each of them for you. Yeah, this is the general statistics. And then, as I told you, we are also coupling our wave model to other Earth system models. Because no model, in reality, no physics solves in silo, right? So they are coupled, they are getting some impact from other systems in the Earth, like with the bottom of the sea or with the atmosphere. So we are also considering if those numerical models have some export field that we can utilize as input field for our model, we can exchange the information dynamically, so we also can send some information to those models. So we are also coupling our model with some numerical models that I'm pretty sure you haven't heard about them, but at Circ, FBCom, Schism, they are very famous circulation model which does the tide, water level variation, and current velocity in the field. And we are coupling the WaveWatch model with all of them. And I think that's it from my presentation, and I would be happy to take questions. I know it's far away from your field of expertise, but I know Osama showed you about tsunami, so I didn't want to show you guys something related to the tsunami. So I picked this topic, and I'm more than happy to answer questions if there is any.
Can we thank the speaker?